Oh,
Can you
I
see
see something.
slides?
Yes, yes.
I see your slides.
Yeah, okay, that's cool.
Yes, I can see those slides. Okay, I guess we have most of people already joined. I think few are missing. Probably they would be joining us momentarily. So we will first go to Jay's presentation. Should be around 30 minutes. Keep your questions for the end of his presentation, and then we'll be having the question and answers for Jay, similar to what he would be seeing in his defense next week, Thursday. The main purpose of this meeting is actually for Jay's dry run. Then after that, a few minutes for some updates regarding labs and a potential meeting of the group for next week, which I'll get there after that. So just to make sure that the bandwidth is reserved for Jay, I'm going to ask you to, first of all, mute your microphones. Everybody, please mute the microphone so that we don't have background noise. And we can mute the cameras now just to allow the bandwidth to be used for Jay's presentation. And as soon as Jay starts his presentation, I'm going to record only the part that has to do with his presentation, the half an hour, and then stop recording after that. And I hope everybody is okay with that, including Jay himself.
Okay.
Okay, the floor is yours, Jay. You can start.
Okay. Good afternoon. Thank you all for coming to this meeting to give me a chance to do this dry run. Okay, so I'm gonna start my presentation. My name is Jay Wang, and the title, my thesis is development of corrosion-resistant coating and corrosion fatigue model for magnesium alloys. In fact, this work is focused on corrosion fatigue model of the coating magnesium alloys. But because before modeling the corrosion fatigue model, behavior of the coating magnesium alloys, we need to deposit a surface coating on the magnesium alloys. So attention was also paid to the investigation of surface coating. Why I cannot? Sorry, Prof. I cannot change my slide.
Are you using two monitors?
Two monitors.
Maybe you want to come out of this presentation mode and then reload it, or going back to the presentation mode and see if the problem is solved.
Oh, okay. Okay. I think it's okay now. A brief outline of my presentation are as follows. First, I'm going to present motivations and objectives of this study. Then I want to talk about my work from two sides: experiment study on corrosion fatigue of the coating magnesium alloy, and computational modeling on corrosion fatigue of the coating magnesium alloy. Finally, I will give the research contributions, conclusions, and recommendations for the future work. So why magnesium alloy? Since corporates average fuel economic requirements stipulate increasing fuel efficiency and reduce gas emissions year after year, magnesium alloys one of the effective ways of achieving this is the lightweight design of vehicles. Magnesium alloys are considered to be an excellent choice due to its low density. The weight savings for equivalent strings using magnesium alloys can be up to 85% with respect to steels. According to a project funded by multi-material lightweight
Hey Rob, how's it going?
vehicles,
Good,
around
good.
50% mass reduction
I am not, no.
could be achieved. Here is the material makeup for the
Yeah.
body in white and
No, I'm not.
crucius design.
Nice. I do have a
As we
twin,
can
but he's
see,
not on the 400. I actually have an identical twin, yeah.
47.5% and 48% mass
That would be
reduction
funny,
could be
yeah.
achieved
That
after
happens a
more use
lot,
of
actually. It
magnesium
happens more than
alloys.
you think.
However, as compared to other engineering
Yeah, I can't
methods,
complain.
magnesium
Same
has
COVID
the
stuff that
lowest
everyone else is
corrosion
dealing with.
potential, and the oxidizer film formed on the magnesium surface was not
You should have honked
as
at
protective
person
as
then.
that in aluminum alloys. So
Alright,
high
take it easy,
corrosion
man.
susceptibility of corrosion of magnesium alloys restrict their further application. As compared to the general corrosion of magnesium alloys, the most dangerous and common corrosion modes include galvanic corrosion in contact with other metals and corrosion pitting for the case of passivating alloys or alloys with a surface coating. Both of which are localized corrosion and are more dangerous because they could act as stress concentration sites to initiate crack under cyclic loading. Consequently, the fatigue strength and corrosion fatigue life of magnesium alloys would be significantly reduced in an aggressive environment. As can be seen from this stress over cyclic fitness curve produced by the Lieutenant test using this cylindric specimen. Surface coating is considered as one of the effective ways to prevent the corrosion of magnesium alloys. It provides a physical barrier between the corrosive environment and the magnesium substrate. But most of the protective developed protective coatings are for load-free applications. Right now, the corrosion issue of magnesium alloys actually is almost solved by various surface coatings. But for the but in real service conditions, especially for automobile structures and components, are commonly exposed to cyclic loading and the corrosive environment. Therefore, the corrosion fatigue is actually a bigger challenge for the extensive use of magnesium alloys. So, based on the current research status, the research gap and objectives are as follows. First, we need to identify a robust surface coating for the investigation of corrosion and corrosion fatigue of magnesium alloys. Secondly, we need to get a full understanding of the mechanism of corrosion fatigue for coating magnesium alloys, such that we could propose a suitable model to predict the corrosion fatigue life of the coated magnesium alloys. Generally, magnesium alloys are industrially used with the surface coating. Various surface coating have been proposed to protect magnesium alloys, such as anodizing, chemical conversion coating, plating, and cold spray. Each one with their own advantages and limitations. Other two students in our research group, Savage and Yuna, have researched on cold spray and ML coating, both of which could significantly improve the corrosion resistance of the magnesium alloys. For myself, I focus on the chemical conversion coating, not only because it is the most widely used method in industries, but most importantly, this method can be easily implemented in our lab, so I can easily realize the control of the quality of the surface coating. However, the currently used chromic conversion coating has inevitable environmental issues. So I choose the environmentally friendly manganese phosphate coating, which is reported to have the potential to replace the chromic conversion coating as my research coatings. Next, choose the investigations on the manganese phosphate coating. Here shows the effects of immersion time on the coating surface morphology with the pH value, best pH value fixed to 1.8 as room temperature. As we can see that after just 45 seconds, there is a thin coating formed on the magnesium surface. And with the extension of the immersion time, the coating became thicker and a big crack appeared after 90 seconds. The corrosive solutions could easily penetrate to the substrate through these cracks. After 90 seconds, the cracking issue became severe, and from the result, from the ASME images, the optimal immersion time seems to be 70 seconds. And the polarization curve obtained by this machine was used to explain the corrosion performance of the surface coating. This curve shows the corrosion potential and the corrosion current density of the surface coating. Generally, the higher corrosion potential means higher corrosion resistance. As we can see that all coatings have higher corrosion potential than the bare alloy, showing the improved corrosion resistance from the coating. And the optimal immersion time is indeed 70 seconds, as can be seen from the corrosion potential for each treatment time. Similar studies were also done on the effects of best pH value and temperature on the coating properties, but not be present here because of the time limit. Anyway, from the study on the effect of processing parameters on the coating, we know that crack-free thick coating with high corrosion resistance is difficult to be obtained by a single conversion process. So to achieve this goal, I developed a two-stage conversion process. The idea of this process is as follows. This is the magnesium substrate. First, immerse this bare alloy into a low pH bath for around 65 to 75 seconds. In this process, the bare alloy will be covered by a layer of magnesium phosphate coating with high thickness and few large cracks. after washing in the pure water, then we put the same sample into another solution with a higher pH value for like 10 minutes. By the second batch treatment, a thin and dense coating would be deposited on top of the thick coating formed in the first step. Guided by this idea, we developed a two-stage conversion coating. Here shows the as images shows a comparison of this the surface morphology for the bare alloy, the coatings obtained by single conversion process and the two-stage conversion coating. We can see that with acceptable shallow cracks, the coating, the thickness of the two-stage conversion coating is higher than the two-stage than the other two single conversion coatings. And besides, EDX results show that some manganese oxide, which are more corrosion resistant than the manganese oxides and aluminum oxides, were generated in the two-stage conversion coatings. This indicates that this two-stage conversion process may further improve the corrosion resistance. Electrical chemical test results also verify this tendency, but not shown here. The result. The source spray test was performed to further validate this result. This was the optical images of the coated samples after being exposed to this solution for 4 days and 7 days. The adhesive epoxy resin is used to seal, avoid the edge effect, so we only observe the central error. As we can see that this two-stage conversion coating has less corrosion pits and obviously shows better corrosion resistance than the bare alloy and other two single conversion coatings. The manganese phosphate coating cannot be used without a top coat in industries because it is too thin. So e-painting and powder coating were both used as a top coats in my work. Let's say the e-painting first. E-painting has advantages such as low cost, low line of sight limitations, and the capabilities of coating complex parts, and so it is commonly used in industry now. This table gives all the coating samples, including the e-painting on top of the in-house manganese phosphate coating, and e-painting on top of some commercial coatings from nearby company. A scribe was first given to each coating sample, so that we can know the adhesive property of the top coat to the subcoating in the corrosion test. As we can see from the result, after 7 days, all the coating samples were corroded. But specifically, for the alloys with pre-treatment manganese phosphate coating, clearly shows better performance than those alloys with e-painting alone, as we can see here. So to identify a robust surface coating, some commercial coatings were also adopted, but from the results, it seems like the the commercial coatings were not comparable to the manganese phosphate coating, except for this chromic conversion coating. Then let's say the powder coating. Powder coating is reported to provide high general and it should better corrosion performance than the manganese phosphate coating. And for the research purpose, the environmental issue of the chromic conversion coating was temporarily not considered here. And this is a corrosion test without a scribe. As we can see that after 21 days, the coating, the powder coating starts just peeling off from some local edges. And when the test time up to 28 days, the corrosion issue was still insignificant. Until 35 days, severe corrosion occurred. But afterwards, I found that this is because of the hole that was drilled for powder coating was not carefully covered by the plasticine I used. If covered well, as we can see, there is almost no corrosion even up to 77 days. To summarize, the ZK60 alloy with ML coating shows the best performance from the perspective of the visual observations and the weight loss as the exposure time. When giving a scribe to the to each coating sample, we can see that there is almost no powder coating period of even up to 35 days, which is much better than which show much better performance than those alloy with e-painting. But we could still see a neat creep of the scribe. See, as you can see here. To summarize, the ZK60 with chromic conversion coating shows the best performance. So after investigation and evaluation of the corrosion surface strategies, I performed corrosion fatigue test for some of the coating samples. As we can see from this image, the e-painting with and without manganese phosphate coating could significantly increase the fatigue strength of the AZ31 in the solution containing 3.5 sodium chloride solution, but not to the level of that in the air. However, not all the surface coating could improve the corrosion fatigue strength. As we can see here, the corrosion fatigue strengths were even degraded as compared to the alloy. For the case of MGC, the ML coating treated for 5 minutes and 10 minutes. In addition, the cold spray, as we can see that the cold spray 75 with e-painting could improve the corrosion fatigue strength to the level of that in the air. So next we are moving to the computational modeling on the on the corrosion fatigue of the coated magnesium alloys. First, I would like to give a literature review on corrosion fatigue model. Corrosion fatigue is, briefly speaking, corrosion fatigue is a fatigue in corrosive environments. The corrosion fatigue process generally occurs as like this animation. First, corrosion pits generated on the surface of the sample. Then, with the corrosion pits grows to a certain size, the crack would be initiated and propagated to the final fracture. So for modeling of corrosion fatigue, the modeling of the corrosion fatigue would be divided into two parts: the modeling of corrosion fatigue crack initiation and corrosion fatigue crack propagation. And the total corrosion fatigue life would include the initiation life and the propagation life. So let's say the modeling of corrosion fatigue crack initiation first. This images clearly see how the crack initiated from the corrosion pit. So the modeling of corrosion pits, that is a corrosion fatigue crack initiation, has been largely researched, and there is actually no big difference for different methods. So I adopted the most common model in literature. Here I briefly describe the used model. In this model, the corrosion pit is modeled as a semi-ellipsoid. The aspect ratio lambda, parameter lambda, is to characterize the size of the corrosion pit. From these two equations, we could get a p depth as a function of time. In order to calculate the crack initiation life, we need to know the critical p depth, where the pit was transited to a crack. In the pit to crack transition point, the shape of the pit is assumed to be a notch, and this transition would occur when the maximum applied load exceeds the theoretical material strength. Here, the Kt is a stress concentration factor near the pit crab, which is a function of the pit depth. So we could determine the pit depth, critical pit depth, and hence we are able to predict the crack initiation life. Before we move to the modeling of corrosion fatigue, I would like to look at the modeling of fatigue without corrosion. The fatigue is a process which causes prematurely reversible damage due to cyclic loading. This diagram shows one of the popular mechanism, fatigue mechanism. This is the crack under tensor stress. In this stress horizon cycle from A to B, the crack tip is gradually bounded due to the significant slip emissions along these slip systems, causing the separation of the materials and new crack faces. Then when under compressions from B to C to D, the slip direction would be reversed, making the newly cracked faces crash into the plane of the crack and regenerates a sharp crack again. Hence, the crack would be gradually advanced by this blunt resharpening process. And this SEM images correspond to above graphs respectively, and we can clearly see the slip bands here, which support this fatigue mechanism. Inspired by this mechanism, some fatigue crack growth models are proposed. Those models are classified into two categories. One is based on plastic accumulation model, and another one is based on linear elastic model. And these two graphs show the crack body and corresponding stress distribution near the crack tip for the two types of model. Plastic accumulation based model have considered the local yielding near the crack tip because of the existence of large stress concentration effects near the crack tip. But in fact, mostly the plastic zone is very small compared to the crack length. So it can be almost neglected. So in this study, we prefer to use linear elastic theory to analyze the stress distribution ahead of the crack tip. Here is the stress expression at a point near the crack tip, and the stress intensity factor range in these equations characterize the influence of the applied stress and the geometry of the crack, and hence this delta K is considered as a driving force for the crack growth. In the case of cyclic loading, stress intensity factor range is used. Based on this linear elastic fracture mechanics, the well-known Paris law, and some other evolved equations gives us a quantitative handle on the crack growth rate. Then, as to the modeling of corrosion fatigue, let's say a special case. Stress corrosion cracking is actually a case of corrosion fatigue with the stress ratio equals to 1. By definition, stress corrosion cracking is a progressive fracture under tensor stress in a cross-section environment. So the stress corrosion cracking should play an important role in the corrosion fatigue process. In addition, the corrosion can decrease the fatigue properties in turn. As we can see, the stress can also enhance the corrosion rate around the crack tip. It can be seen after the application of the loading, the corrosion rate was enhanced from around 0.112 to 0.18. So it has been fundamentally acceptable that process interaction between the corrosion and fatigue causes much worse consequences than any single or summation of these two processes. And similar to delta K in fatigue, stress intensity factor K is regarded as a driving force for this stress corrosion cracking. And this diagram shows the general curve shift of stress corrosion cracking velocity as a function of stress intensity factor. And from literature, this curve can be expressed by this equation with different parameters A and N. in different regions, especially for the region 2, stress corrosion cracking is independent. It's independent to stress intensity factor. And right now, three types of corrosion fatigue model are reported in literature. The first one is a superposition model. Originally, this model claimed that corrosion fatigue is a simple summation of fatigue and stress corrosion cracking. This model ignored the interaction of fatigue and stress corrosion cracking, and hence underestimated the crack growth rates. An interaction term was introduced into this equation afterwards, but this term was practically difficult to be quantified. The second model is a completion model. This model assumes that fatigue and stress corrosion cracking are mutually competitive, and the corrosion fatigue crack will propagate at one of the faster rates. The model tends to be effective at high frequencies and high stress intensities. These two models were initially developed for aluminum alloys and steels, which tend to be acceptable to stress corrosion cracking at high intensities. The third model is a process interaction model. It is assuming that fatigue process and stress corrosion cracking are interacted each other, which is more suitable for those alloys which are more susceptible to stress corrosion cracking, such as magnesium alloys. So this model I propose is based on the process interaction model, but the role of the stress corrosion cracking in this model was not well defined. So in my proposed model, the role of stress corrosion cracking in the contribution of corrosion fatigue crack propagation was step by step considered in the whole process, in the whole corrosion fatigue process. Next, I'm going to talk about this new model. This is a graph showing the comparison of fatigue crack growth rates against stress intensity factor range in inert environments and corrosive environments. The fatigue in inert environments is basically considered as a baseline to model the corrosion fatigue crack growth rates through either approach A or approach B. In the new model, these two approaches are combined together. For the driving force of corrosion fatigue, delta K and K max are regarded as a unified driving force, which is different from the previous, only one driving force in previous models. As can be seen from this diagram proposed by Vasudevan, every point in this curve represents the same crack growth rate, which is controlled by the delta K and K max. With respect to the pure corrosion fatigue, equivalent fatigue crack growth rates in corrosive environments leads lower stress intensity factor range and lower Kmax. Overall, this corrosion fatigue crack growth rates in the proposed model is a function of delta K and Kmax, and it is contributed by the stress corrosion cracking. Based on the characteristics of stress corrosion cracking and the process interaction model, modeling of corrosion fatigue crack propagation are divided into three parts. First, before Kmax in the cyclic loading reaches reaches the KISSA, which is a threshold value below which there is no stress corrosion cracking. The corrosion fatigue crack propagation are only contributed by fatigue as expressed in this equation. The parameters beta and gamma are representing the effects of the corrosion on the driving force and the material properties. Secondly, when the Kmax exceeds the KISSA, stress corrosion cracking starts joining with fatigue to contribute to the corrosion fatigue crack growth rate as expressed in this equation. Finally, when the Kmax further increase into the KPL, which about which stress corrosion cracking is independent to the stress intensity factor. And there is no influence of the stress corrosion cracking on the driving force, but the effects of the stress corrosion cracking on the material property still remains. And next, I'm going to show how we determine the parameters gamma and beta in the proposed model. In the first region, crack growth rates could be expressed by this equation. First, we need two set of fatigue data in vacuum to determine the parameter C, F, M, and the parameter R. As two different stress ratios, the driving force for the same crack growth rate should be the same. So alpha can be obtained using this way. After we here it is worth to note that for some materials this parameter alpha is a constant, but for some other materials this may is a function of some other factors, like in this case is a function of effective stress intensity factor range. After we get the alpha, the fatigue data as different stress ratio can in fact can be collapsed into one curve. Through linear regression analysis for the curves for the collapse line, we can get the parameter CF and gamma. Then the parameters gamma and beta are superimposed in this equation to explain the corrosion fatigue growth rate. In order to determine them, one set of corrosion fatigue crack growth rates is required. For any 2 points in this line, substitute the crack growth rate and corresponding stress intensity factor range into this equation. We can get to equations with two unknown parameters. So we can determine a set value of beta and gamma. By repeating this process, we can get more set values of beta and gamma, so an average of them can be obtained. For the second part, the equations will be used by the second equation will like this. So we cannot calculate gamma and beta by the same way. As an integral of the stress corrosion cracking is introduced in this equation. So the recommended way to determine them is by a numerical integration method using a computational program. So in fact, the parameters gamma, the value of parameters gamma and beta is different in three regions. So we use some published data from literature to validate this model. Here is a validated results for 43, 40 steel. At this moment, we assume that the parameter gamma and beta for the three regions are the same for the simplicity of the modeling. The red point is the predict data by the proposed model, and the black point is the original data. The data predicted by the superposition model was also presented as a comparison. As can be seen that this proposed model provides a better agreement with the test data. Validations using other kind of 43, 40 steel and titanium alloy and aluminum alloy was also present here. All the validations using the proposed model shows very good agreement with the test data. So that is all the research work on the corrosion fatigue model of the coated magnesium alloy. From the work, we investigated the corrosion and corrosion fatigue performances of magnesium alloys with various coatings, and I developed a normal stage conversion process to obtain the defects and the second phase particle-free corrosion-resistant surface coating. Also, from this work, we identified a two-layer corrosion protection strategy for the forged ZZ80 and ZK60. Most importantly, we propose a corrosion fatigue model for the prediction of corrosion fatigue life of mechanism of various metals. This is the conclusions. I'm not go through each by each for the time. So for the future work, because for the we already modeled the corrosion fatigue crack propagation of magnesium alloys, but for the corrosion fatigue crack initiation, for the verification of the corrosion fatigue crack initiation, we need data to verify this model. So for the future, we need to perform some tests to collect data about the corrosion fatigue crack initiation with for the coated magnesium alloys. Also, because we only use the published data to verify this model, we don't have any data for magnesium alloys to validate this model. So we need to conduct some tests to get some corrosion fatigue data and stress corrosion cracking data to finally apply this model to the magnesium alloys. Yes, that's all my work. Thank you.
Hey. Okay. Thank you, Jay. So in terms of timing, you are well over 30 minutes. You are around 45 minutes mark. So, that's about 15 minutes more than what you're allowed. But I wouldn't be much worried about that because more number of time you're trying this, it will be much smoother and much faster. And I think there are many areas of reducing, the time you spend on some of these slides, so that that it can help you with the timing. Okay, now the floor is open for question and answer. So if you want to make a question, we can do it two ways. Either you can raise your hand. You can see on the participant there is something that shows raise hand, or just unmute yourself and just ask question. And I'm going to stop recording now. Okay. Who's going to be the first in terms of asking some questions?
Okay. Hi, everyone, and a nice job, Jie. My question is, I didn't notice whether the frequency has been taken into account in your model or not, because I guess unlike simple fatigue, in corrosion fatigue, it has an important effect.
Yes, actually, the effect of frequency was considered into this model because the effects of the frequency can be realized from the from this term, as we can see here. We have a term that's considering the frequency.
Yeah. Okay. Yeah. Thank you.
So yes, we definitely will consider the effect of the frequency on the corrosion fatigue.
Okay. Yeah. Thank you very much.
Okay. Amir?
Hello, everyone. Thank you, Jay, for the presentation. I hope you will respect the time in your final presentation. My question is regarding page 5, where you show the SN curve. First, I'm not sure, is it a conceptual figure or it has a reference? You didn't mention a reference if it has actual one. The other one was that the numbers in the x-axis, are there actual life? For example, 10 to the power 9?
I beg your pardon?
I'm expecting to see maybe 10 to the power 7 for the fatigue limits, although sometimes they go further, but I'm not sure if the x-axis values are correct.
This is not a stress curve for magnesium alloys. This is it's a graph from a reference. I'm not sure here. Yes, I should give a reference here.
But the x-axis values are correct, yeah?
Yeah. But I'm not sure.
Yeah. It takes.
What this curve is, what kind of materials this is, this curve belongs to.
Okay. Thank you.
Hi, Jay, this is Xin.
Hello.
So, yeah, good presentation, much better than previous times. But still, as we all see, it's relatively long. I would still suggest, although after practice you will improve a lot, I would still suggest you reduce some of the slides, reduce slides number, maybe less than 40 at least. For example, I'm thinking for the corrosion parts, you showed a lot of pictures of that scribe test after the salt chamber test. Instead of that, I would suggest just create a table, include all various kind of combination of coatings you tested, and then a summary of the results, the observations, things like that. Give a summary table. It's easier for the audience to follow and understand your conclusion, other than showing so many pictures there and have no time to discuss.
Yes.
One suggestion. Another thing I feel when you finish your first part, I would suggest you give a little bit more summary of the first part and then a few connecting sentences. I feel the transition from the experimental study part 1 to the modeling part is a bit abrupt, a sudden change, and without really explaining what's the use of your experimental study for your modeling, and or logically how did you think modeling is important? Like some connecting sentences will help.
Okay, I see your point.
So another, and you used 3 kinds of substrate alloy, right? You didn't really specify, you didn't elaborate on the effect of the substrate on the corrosion property, and will they, like when they were deposited with the same type of coating, we see different corrosion performance, and why is that? So maybe in your table summary slide, you can also add a few bullet points to talk about that or summarize findings about that. But here as a question, like, can you elaborate a little bit more on all those important alloying elements, the effects of alloying elements on the corrosion performance of the substrate alloy? This is a question. For example, AC31, you have aluminum, zinc. Generally speaking, what is the effect of those alloying elements on the corrosion properties of magnesium alloys? And how about zirconia?
Okay. For example, for the alloy AZ31 and elements aluminum and zinc will be used to form some second phase like beta phase, some other intermetallic phase, which is which is generally used to improve the mechanical properties of the alloy. But from the perspective of corrosion, the addition of those elements would decrease the corrosion properties of the magnesium, because, for example, the second phase, the second phase, beta phase, there would be large corrosion potential difference between the metric alpha phase and the beta phase, and thus form a micro galvanic cell from which would cause galvanic corrosion. So the addition of the elements like aluminum, zinc, manganese should be carefully adjusted. For example, when the generally with increasing of the elements of aluminum, the mechanical property like the strength would be increased, but the corrosion property may be degraded. But from the research, we also found that once the beta phase due to the large content of aluminum, the beta phase would form a network structure which acts like a barrier to retard the corrosive environments penetrate to the alpha matrix. So there is a balance between the mechanical properties and the corrosion properties by adding those elements.
How about zirconia and manganese? Zirconium. Zirconium, ZR.
Zirconium. From what I know, zirconium is a rare earth element. We can see the example of ZK60. This element should have a positive influence on the corrosion side of the magnesium alloys.
Do you know why?
This is because of the addition of the choline. Also formed a network structure of beta phase that's a little similar to the beta phase in AZ31. It is also can retard the corrosion process by acts as a barrier between the corrosive environment and the alpha matrix.
Not really, because the zirconium we didn't add that much. It's below 1%, and the main purpose is to refine to obtain fine grain size of magnesium alloy. But incidentally, zirconium has a beneficial effect on the corrosion performance because it reacts with some heavy metal, other like iron, copper, and nickel, those impurity elements in magnesium, and remove the impurities and thus improve corrosion performance. There's a good review paper actually on the effects of all these elements. I would suggest you must have seen that. I suggest you go back and look at that and prepare those. So, because you have to know those basics so that you can really give an in-depth explanation or the corrosion behavior or the bare substrate and with coatings.
Okay.
Yeah. Thanks.
Okay. Andrew?
Sure, Jay, great job. I just want to echo some of the comments that were previously mentioned. I had a question regarding your literature review slide. There is no slide number on it, but it's the one where you had the three models that you proposed, or the three models that you were reviewing.
Yeah.
One was a superposition model, I think a competition model, and then, yeah, the process interaction model. So I had a question, it's more of a high level question regarding, let's say, model one.
Okay.
My question is superposition valid, or do you utilize it as an assumption in your proposed model? Like they're clearly divorcing the effects of stress corrosion cracking from, let's say, the pure corrosion fatigue. Is that something that you're assuming in your model, or are the synergistic effects of each individual corrosion term, are they not, is superposition not valid?
In my model, corrosion fatigue crack growth rate is not a simple summation of the pure fatigue and stress corrosion cracking. Each term, like for example, the pure corrosion fatigue, because it is a process interaction model, so the pure fatigue was influenced by the stress corrosion cracking, and also the stress corrosion cracking also influenced by the pure fatigue. So I made a modification for each term in this equation.
Okay. I would maybe recommend that the process interaction model highlight the fact that your proposed modification is definitely a process interaction model, and that provides value over, like you said, the simplistic summation of individual terms for the superposition model. Yours, I think, is more complex than that. So maybe highlighting that a little bit clearer would be useful to the audience.
Okay. Thank you for your suggestion.
Okay. Any other questions for Jay?
Hi, Jay, can you go to your slide number 22?
Okay.
That's 26.
Okay.
Is this 22? Further back? Maybe
Yes.
number 20? Not this one. I was seeing that there was one showing the results, ZK60 and maybe 21. Next one. Right, yeah. Like from this, the final result, right, day 77, it looks to me AZ80 with the coating has better resistance because I don't see any corrosion sign on the sample after 77 days. But why did you drew the conclusion that ZK60 shows the best corrosion performance here?
First, from the weight loss as a function of the exposure time, the ZK60 with MLO shows the least weight loss. And another reason is, although you can say the AZ80 shows better than the ZK60 in the test day 77, but I think and this mostly because of the coating, because of the coating, the powder coating homogeneity, not because of the coating itself. Okay,
I don't really get your point, actually. So you measure the weight loss.
Yes.
You're saying 60 has a lower weight loss of sample.
Yes.
Not so convinced. Maybe we can discuss offline. But I start to have a second thought about this. Maybe at least we can say AZ80, AZ60 may be comparable, like similar corrosion performance. Maybe. Not so
yes, that's a.
I'm just saying, like from this picture, quite straightforward. We see AZ80 is better, because if you choose to show this result, it causes questions. Maybe you draw the conclusion from a combination of various kind of results that's come to the conclusion. But if you present it this way, it will raise questions. So we can talk offline to see what will be a better way to present this result.
Okay. Actually, I was wondering if there is necessary for to present the test results, the correlation test results without the scribe, because for comparison there is no correlation test without the scribe for the e-painting.
So without scribe, you were saying almost no corrosion for all samples. There's no
Yes.
differences.
I mean, for e-painting, we don't have test results for corrosion test without a scribe.
Yeah, I agree that for the e-painting, since you don't have the other corrosion results, I don't think you need to bring that in your presentation. It's in your thesis. However, the ones that you had with this polymer type of coating, you have both without and with the scribe testing. That would be enough.
Okay. Yeah, because the content is too much. I thinking to cut some slides, but I'm not sure which slides should be cut.
Yeah, that's what I mentioned. If you give a summary table, list all the tests, all the conditions you've tested, then you don't need to show all the raw data.
Yeah, I think that the e-painting one you can easily take off from the presentation, and it's not just a matter of removing some of the slides where there is a good chance of doing that. It's the amount of time you're spending on some of these slides that can be shortened rather significantly. I was just coming up with a time budget for your presentation. If we divide that to 4 sections, the whole presentation. One is the what I call front matter, where you talk about the title of the thesis, the background, and the motivation. That's the first part. I think you should not be spending more than 5 minutes on that. So you need to budget your time as far as these front matters, especially talking about motivation and many of that background information that you're providing. I think that needs to be shortened to 5 minutes. What's the most important thing? Bring it out. The rest of it, try to shorten it. So that's the first part of your presentation. I think there are 2 main part of your presentation after that. After the first one, the second part is that you have to go over the work that you have done on developing the coating and the testing you have done for verification. This slide would be one of them. So I would spend 10 minutes for that. Because I think the greatest contribution that you have is on the modeling side. This is also very good contribution that you have. But especially considering your external who's coming from the modeling side, I would say for this part that you are developing the coating and you're doing corrosion tests and you're actually showing that it works, I would budget 10 minutes for that part. So 5 minutes up front, 10 minutes, you are halfway down now. For the second part of your contribution, which is the modeling, I would put something around 13 minutes there, where you probably can shorter your talk on some of the background slide on that side, especially when you're talking about stress intensity factors and things. That animation was very good to give us what are you doing and why is it important. After that, you bring some background regarding the fracture mechanics, which probably you can summarize that in half a minute or 1 minute, and then go right into your own model. And I think you did a very good job in describing what your model is, in presenting the result, comparisons, and everything. So that part was very well done. You may need to do some practice to bring it down to 13 minutes. And the last 2 minutes, I would leave for just going over the main contribution you had. That is slide, I think, 44 that you had. I wouldn't put up a slide on conclusion and suggest that you go ahead and read it. I'm not going to talk about it. So if you're not going to talk about it, don't bring it up. But I think you need to bring up that conclusion has to do with your contributions. So I would very simply put three or four conclusions up and have the keywords and just go over them very quickly. You don't need to make any reasoning because you've already done that. And I would spend around a minute on the future work. I think that is a key in what you're doing, because you're saying that I have developed that model, I have developed that coating. The next natural step after verifying my model is to apply it to magnesium, and especially coating on magnesium, which would require these next steps. And then you go very quickly over the things that needs to be done, which is mainly experimental, and there's nothing in the literature that can be used, and that kind of lays out the next step for the next students who would be doing these things. So 4 parts, 5 minutes, 10 minutes, 13 minutes, and 2 minutes. And you gotta constrain yourself into those timing budget. Otherwise, you will end up yourself spending 15 minutes on upfront stuff, and then another 15 minutes on the next one, and another 15 minutes on the last one, which was the 45 minutes that we have. But if you consider this budgeting, I think you should be able to do it. I'm pretty sure you'll go back, look at the recording that we have, and you find lots of areas that you can cut in terms of the description that you're verbally giving, and would be more fluent in delivery as well. So, a good 5 to 7 minutes will be cut just by repeating what you have. Another 5 or 7 minutes you have to cut from here and there. And I think that budgeting is a proper way of doing it. Now, that was a long comment. Now I have a question. If you go to slide 43, I believe. Yeah, okay, that's good. Right there. So if we look at your results, which are in red, and test results, which are in black, would it be fair to say that your prediction are relatively very good, where we are dealing with higher stress intensity factor range, and at lower range they tend to deviate from the test results? Why?
Because I think that's because of the use of the same parameters gamma and beta in the 3 regions. We should from the proposed model, we should use different set of beta and gamma values for different regions. So from this picture, we could clearly see the need to use the different parameters for the 3 different regions.
Okay. I may generally agree with you, but have you done that to show if you use different gamma and beta for the three regions that you have, you would get closer to the experimental data?
Actually, I tried, but I didn't get the results.
What does that mean? You didn't get the result, meaning that you were not able to find three independent value for gamma, beta related to these three regions that you had, or you had that, but the results did not change.
No, I actually didn't finish the whole process to find the three different values of parameters gamma and beta.
Mm-hmm. Mm-hmm. Well, I know the details of what you're doing, so I'm kind of convinced why, but I don't believe that the readers and the audience would necessarily agree unless you kind of either corroborate that answer with some results or say what would happen or how would beta and gamma be more favorable in those two other regions if you were going to choose them independently and not just use one set of parameter for the whole process.
You mean I gave other results with